of solute per liter of solution. So for example, in this case here, if we knew the volume of this reaction container and we knew the concentration, we could figure, we knew how many solute molecules are present, we could figure out the concentration. So for example, note that we have 4 reactant molecules in here right now. If we put 2 more in there, have we increased the concentration or decreased the concentration? You have what? It increased the concentration. Okay, note that we have 6 of these balls in here. Let's say we make this container bigger now. Have we increased the concentration or decreased the concentration? You what? It decreased the concentration. Okay, so again, in the first case, we went from 4 reactant molecules to 6. We're increasing the numerator, which means we're increasing the concentration. We went from this size container to a bigger size. Note that we're increasing the denominator and then decreasing the concentration. Okay. And then for a catalyst, does anyone know what a catalyst does? Yeah, so it's a substance which speeds up the rate of reaction. So we'll talk more about that. Okay, so going back to the question, which of these 3 factors increases the energy of the reaction? So is it temperature or concentration or a catalyst? Okay, so who says that temperature increases the energy of reaction? Who says concentration increases the energy of reaction? Okay, so if we increase the temperature, are these reactant molecules moving faster or slower? Faster. So does that mean that the energy is going up or down? Yeah, so for question 1, temperature increases, or increase in temperature increases the energy of the reaction.
Well, what if you have a certain small amount of like NI3 and then that makes it small, but if you have a lot more NI3, it's a bigger explosion, right?
Yes, that actually has to do with question 2. Which factor increases the frequency of the collisions?
That's more.
Yeah, so for that second question, which factor increases the frequency of collisions then? Yes, it's going to be concentration. So note what happens here. If we have, in our original picture, we had 4 reactant molecules. There's going to be a certain number of collisions. But if we increase that number, we get more collisions or fewer collisions? We get more collisions.
What if you have 6 at a certain temperature? They're colliding a certain amount of times. If you have 4 at a higher temperature, they could collide just as many times.
Yeah.
So.
Yeah. So that's how you can vary or change those 2 factors to control the reaction rate. Okay. So you can adjust the concentration or the temperature or both to to control the reaction rate. So again, this is what happens, when you're driving in the middle of the night at 2 a.m. in the morning with no cars on the road, the frequency of you colliding with another car is going to be very, very low. However, if you're driving at 5 p.m. on a Friday afternoon, when everyone's trying to get home, there's a lot of cars on the road, concentration increases, so the probability of a collision increases. Let's go back to our wood burning reaction again. So we know that this reaction is exothermic. I'm not sure you see this picture. This picture on the side, it says, this is the mother of all speed bumps. So this is a road. Look at that big speed bump. Check this out. I got it posted on the website. I'm not sure where I found this picture, but anyway, I found this thing. This is a good one for for activation energy. So in this case here, is the activation energy, the speed bump, large or small? Okay, so in this case here, notice you get a big speed bump. For this wood burning reaction, we said, is this reaction fast or slow?
Fast.
Yeah, fast. So would the speed bump or the activation energy be big or small? Yeah, so small. So for activation energy, if you have a small activation energy, this tells you have a fast reaction. If you have a large activation energy, it's going to be a slow reaction. Okay, so which reaction energy diagram represents the wood burning reaction? Is it the one on the left, this one, or the one on the right? That one. Okay, so does this one better represent the wood burning reaction or that one? Okay, so who says this one? Who says that one? Okay, so those who said this one, this should be this one. Note that this has a small activation energy. So on our graph and our diagram here, so let me erase this part here. Okay, so note that the activation energy is represented by this is our speed bump for the reaction. So this energy here, this is the activation energy. And that symbol, the symbol for activation energy is EA. Okay, so again, on this diagram, note that this energy here from there to there, that's small, but from here to there, that's very large. Okay, so again, that's going to be your activation energy. And then to answer this question, how can this reaction be slowed down? Yeah, so less energy input, which means we can lower the temperature, okay? Or we can slow the reaction down by decreasing the concentration. We can use less wood. Now, when you burn wood, note that if you just have, we know that when you burn wood, the wood just burns. But you have to get the burning process started. So what's happening there is that you have to heat up the wood. When you're heating up the wood, all that's happening is that you're making those molecules move faster. And when they move with sufficient speed for those collisions to break bonds, that's when the wood will start burning. Okay, so that's that activation energy. When you're heating up the wood sufficiently so that once that speed bump is overcome, then the wood's going to burn and you'll start producing products. Okay. So note that if you have a large activation, it takes a lot of energy to overcome that barrier to get to the other side. Okay. And then in that case, that reaction will be slow. Okay, we looked at that iron rusting reaction, that picture just a few minutes ago. So what does the reaction energy diagram for the iron rusting reaction look like? Is it the one on the left or the one on the right? Okay, so for this one here, is there a small activation energy or large activation energy? Small. It's small. For this one, is it large or small? Large. Is this reaction exothermic or endothermic? Exothermic. Is this reaction exothermic or endothermic? Exo. Okay, so Is the iron rusting reaction fast or slow? So that means that the diagram which best represents the iron rusting reaction is the one on the left or the one on the right? Yeah, the one on the right. What does the reaction energy diagram for the diamond to graphite reaction look like? Is it the one on the left or the one on the right?
Right.
It's also the one on the right, because note that this diamond to graphite reaction is very, very slow. Yeah, we actually, according to those diamond miners and diamond makers, they want this reaction to be very slow. So according to thermodynamics, this reaction actually occurs spontaneously. Diamond does actually convert to graphite, but this reaction is so slow that the De Beers company came up with that slogan, "Diamonds are forever." Advertising Age magazine called that slogan the best slogan of the 20th century. And they made tons of money with that slogan. Anyway, that's because this reaction is so slow. Okay, so we can quantify how fast the reaction occurs. So in physics, speed or rate is given by the change in distance with time. In chemistry, it's the change in concentration with time. So note that according to this equation, the concentration of either reactant or product is changing over some time period. So we can actually graph what this looks like. So note that on the y-axis we have the concentration of wood, 1 over reactants. On the x-axis is time. What would this graph look like? So I'll give you a few choices here for this graph. Okay, so this is the concentration of wood. Okay, so does the graph look like this, or does it look like this? Does it look like that, or does it look like this?